So one of the common things I wanted to solve, one of the most important things, was that I wanted to have one way of scaling both up and out. They are essentially both, but scaling up, I mean scaling out on hardware. Scaling out in a single machine, on a multi-core box, right? There's also scaling out. It's just that instead of having multiple machines, as you have in scaling out like horizontally in the true sense, you're actually scaling out on multiple processors. And I mean, which you do where and when shouldn't really matter, I think. That's something that you should actually externalize into a deployment decision. That's basically how your topology should be. So that was one of the key design things I wanted to do, and that I saw missing. The people use different tools for like dealing with concurrency and different tools for dealing with distributed computing. So how do we achieve this now then? So we use something called actors, right? And actors is the sort of the common theme throughout this talk. Akka is much more than actors. Actors is one, as we call it, one tool in the toolbox. It's a great tool. It has, I mean, lots of applications and use cases, and you can solve, I think, 80% of all the problems that I see out there using actors. But the other 20% are hard to solve with actors. It's not a silver bullet, and that's why we have many other tools that I will cover by the end. Just mention them briefly. But this build cornerstone in Akka is message passing concurrency, as it's also called, actor-based programming. So what is an actor? Yeah, I'm not talking about actors like John Goodman, even though I mean at our team we have a common sort of reoccurring event where we watch this movie, The Big Lebowski. Instead, what I mean is that, so at the base level, an actor is the code of the unit of code inside an actor system, and of course then in Akka. It has similarities with like classic JEE, serverless, session beans, etc. It's a model for like organizing your code, externalizing out like things like deployment policies, deployment decisions into a configuration file. Actor is nothing new. It's been around since like 1973, coined by Carl Hewitt in a paper. You can look it up later if you're interested in the history. It was catched on like at the sort of real world level by Erlang in the early 80s, and have been used for 30 years in the telecom industry, using the Erlang programming language and other sort of less or more obscure languages, right? But the ideas are extremely sound, regardless of implementation. And I think that we have a lot to learn there in the sort of how we solve problem in the Java enterprise space, or Scala, or whatever you use, or C#. We're still stuck using the ideas and tools and constructs that are like since we started using sort of like in the 60s, basically, with Fortran and stuff. So I think there is, even though there's really not new techniques, there might be new to a lot of people, but they are old and proven, right? And what actors give you is a way of programming at a higher level. So I won't rant long about like the problems with threads and locks, even though I could. I think I'm just going to leave it at, I think that the way people do, the way we do concurrency in Java, C#, C++, is completely broken, I think. It's the absolutely wrong way of approaching a problem. Since what we do is that we work with things that leaking up all the way from the operating system, right? It's the way the most low-level primitives in the whole hardware stack actually is dealing with the problem. That leaks all the way up to the programming model, and it becomes the default way we deal with problems. In other areas, we work at much higher abstractions. And I think we need to raise abstraction level for concurrency, parallelism, and distributed computing as well. So instead of dealing with this low-level plumbing that you actually have to do when you work with threads and locks, what you instead do is that you think in workflow. You're thinking, how are my messages flowing in the system, okay? And that's business logic, right? Basically, more or less at least. That's how your components interact and how the events like flow and request response and stuff like that. And if you do that, if you design your system around these ideas of workflow, then you get extremely good resource utilization. You get parallelism, concurrency. You get basically deadlock-free code, unless you actually deadlock on a conceptual level. Sure, you can create a deadlock by in the way your messages flow through the system, but then it's actually then you've thought. Then you've done your thinking completely wrong. Instead of that, the plumbing deadlocks. For example, the deadly embrace that you take locks in the wrong order, right? And the bad thing with that is that in Java, if you get a deadlock in Java, then you lost 2 threads. Excuse me. There's no way back. But if it's just in workflow, then you can introduce things like timeouts and get out of the problem, etc. So that is great. It's also on top of all this greatness that I think, with the concurrency and with the extremely high throughput that you can get, like really maxing out on your hardware, it also comes with, I think, a superior model for dealing with failure management and error recovery that we will look at later. Okay? It's also distributable by design. And here comes that, it's actually the same tools, the same components that you're using can be used for scaling up and out, regardless. There's nothing you have to think about. You write your components, right? And then afterwards, you configure if they should run in process, or if one of the parts of the system should run in another machine, etc. We have what is called location transparency. Okay? That it really doesn't matter where your components run. That's something that can even change at runtime. The system can detect that, okay, this component is not ideally over here. It's basically only using resources here. Then the system can actually move the running instance on the fly to bring him closer to the context he's actually used in, or the other way around. So you get scale up and out, like free as part of the model, if you just think and work in actors. And I think this is the perfect fabric for the cloud. It actually matches a lot with similar traits that you have in cloud computing. You have a system that is like inherently elastic. Actors can come and go, same as nodes can come and go in cloud computing, a very dynamic world. You have fault tolerance built in, okay? So the systems can actually heal itself, how we will look in later. And we also added on top of the actor model a lot more, even higher level concepts like load balancing, routing, pooling, and all the stuff you might need. Okay, so where is Akka currently used? Here is a sort of selection of some of the companies that are currently using Akka. And as you can see, it's a big variety of industries. You have like telecom, you have e-commerce, you have investment banking, merchant banking, data simulation, trading, betting, gaming, all kinds of stuff, right? Even more than that, like sort of social media and TV and so on. And the common theme, though, across all of these industries is that they have a need for high throughput, low latency, with very high SLAs, strict SLAs on resilience. Okay, which is actually the whole reason for the existence of Akka. So what can you use actors for? If we now try to take a step back and take what we already know and try to map that to an actor, okay? So you can see an actor a little bit sometimes like a thread, for example. It's a very bad sort of comparison, as we will see, because actors are much lighter than threads and so on. But conceptually, they can be looked a little bit like a thread. They can be seen as an object instance or a more richer component. They can be used as a callback or a listener. They would use like anonymous class or closure. It can be a singleton or represent some sort of service. It can be, instead of being just a single actor, it can represent a router, like it can be working as a load balancer or a pool. It can be very much like a message-driven beans, or even though that's constraining the model quite a lot. And it can represent an out-of-process service, like mocking out something like that. It can be a state machine, as we will see. So actors is a really different beast, right? It can be many of the things that we know. So it takes a while to wrap your head around what's really an actor or what a really actor is. So if we take even a step back, further back and see, look at the definitions. What is the actor model as it's defined by Carl Hewitt, the guy that sort of invented the model? So it's according to Carl Hewitt, it's a fundamental unit of computation, that embodies three things: processing, that's the behavior, the thing that runs, the things that execute cycles on the CPU, right? Storage, that's the state, that's the stuff on the heap, right? Communication. These are the three things that the actor model sort of embodies, right? And we have three different axioms. When a message is sent to an actor can do one of three things. Okay? It can create new actors. It can get references to new actors. It can send messages to the actor it knows, and it can also become something else. It can transform its own internals, its own behavior, its own interface. He's turned himself to something else for the next message that arrives. And this last thing is sort of the whole thing that makes the actor model so extremely dynamic and flexible, that we will look at later. So if you want to break this down into these three different axioms, right? Create, send, become. Become is like we transform yourself. I'm going to add a fourth one that I think belongs into the actor model, even though it's not part of Carl Hewitt's original definition, and that is supervise. That's how the fault model, how you can deal with failure, comes into the picture. Okay? So if we're now going to look at how we can define an actor first, before we start creating and using them. The first thing we do is that we create a message. The message is a greeting class up there. Okay? So a message is the actor's public API. Okay? That is what you can do with an actor. You can send him these methods. It's like, think about messages that can be seen like the methods in an interface, right? That's what the actor exposes. Then you create your actor, and in Java it's just a regular class. You say you're extending. Now we call it untyped actor. In Akka we have two types of actors. We have untyped and we have typed actors. Typed actors actually exposes a statically typed interface. So it's a more statically typed sort of component. You lose a lot of the dynamicity in the model of that, and it's not like the traditional type of actor. It's more like the active object pattern, but some people like that. But I'm going to now talk about the true sort of actors that I think are they're more powerful and flexible. So the only thing you need to do when you create an actor is extend this untapped actor, and then you override the onReceive method. If you've seen the message-driven beans, it looks very much like that. Okay, but don't be fooled. Actors are much more powerful, and they have much richer semantics than message-driven beans. They're not just a callback. Like that basically what message-driven beans are. So here we can receive the message that are sent to us. So then we need to sort of check what kind of message it is. In Java we need to use like instance of. In Scala, our other API, I just have to say, this API looks much cleaner. Scala has pattern matching, so it actually allows you to introspect your objects right in the case statement. You can actually peek into the object directly and bind certain things. So I don't have an example of that now since I'm focusing on the Java API, but it's sort of in Scala it matches better, I think, with the true actor model. From a syntax perspective, it has more like syntactic sugar for these kind of things, basically. Okay, so now we have an actor. That's basically it. So if we now create an actor, okay, actors are extremely lightweight, as I said. You can't think an actor one-to-one with a thread. An actor has about 300 bytes, and so you can create close to 3 million actors on 1 gigabyte of RAM. This means you can easily model things that are extremely hard to model using threads. You can easily have, for example, 10 million concurrent users running in your system at the same time. It's really hard to do stuff like that using threads. So an actor also has very strong encapsulation. It has much stronger encapsulation than classes or instances of classes in Java or C Sharp. They are closer to the original definition of object orientation than classes or instances of classes, right? So they encapsulate state behavior as a regular object, but they also have a message queue, okay? That's what we call the mailbox. So each actor has a mailbox where all the messages are received into the actor ends up, right? So how can we create an actor now? So for the first thing we need to do is we need to create the actor system. Okay, so we create an actor system. That's sort of our application. You can think about it a little bit like Spring Beam Factory. If you use the Spring, or like I don't hardly remember what it's called. It's EGB context or something in EGB, right? So, and then when you have a system, you can use the system then to use the factory method ActorOf. ActorOf creates actors, okay? So but in ActorOf you pass in two things. First you pass in our configuration object called props. It can be a pretty rich kind of configuration, we'll use that later, but here we just tell it what type of actor we want. And we also then give it a name. Names are important in Akka. Out here now comes an actor ref. This doesn't return the instance of greeting actor up here, okay? And that's very important. This decoupling enables a lot of things. First, it's a safety that you want to add public methods to the greeting actor and call them from the outside, like bypassing the whole model and being back to evilness and hell. Shared state concurrency, right? We don't want that. So that's why we return actor ref with a clean API that we can use now to interact with the actor. The other thing is also that we will see that this code is also all we need to run this in a distributed environment. We don't need to change one single line of code. This thing that's returned here, the actor ref, can just as easily represent a running component on another machine, in another data center, or whatever. And what's even more nice, since I only have the reference, it means that the running instance can actually move around, even, all depending on how the application is being used and how the runtime tries to optimize the runtime characteristics. So this decoupling is good, even though it might look odd. Okay? So actors form hierarchies. You remember we said system ActorOf. When I do that, I create a top-level actor that sits right underneath an invisible actor that we call the system guardian that's inside our actor system. Okay? So when you say system ActorOf, foo, then you get a child of our sort of application system guardian. Okay, this is also this hierarchy stuff is very important when it comes to the failure model. But for now, we just talk about it in terms of name resolution. Okay, so now inside this actor foo, there is a member field called context. That is what I should use most of the time. Okay, I shouldn't use system. Because if I create system, I just create a whole bunch of top-level actors, and I'm missing out on all the goodness, right? So if I now use context ActorOf, what I'm doing then is I'm creating a child here of my actor. And if I continue using context all the time from within the actors I create, I'm creating child, and I become the parent of that, okay? So then you get this, like an actor hierarchy, similar to this. So this is important now when we use the name resolution, because we talk about actors as and their names very much like a file system. This looks very much like a file system, right? With a root, and then you have blah, blah. That's exactly how you reference them as well. So foo here, for example, that's /foo. It's a top-level actor in our actor system, okay? This A here is /foo/A, and /foo/A/B, and so on. And we have a method called actor4 that you can look up actors, so you can get reference to actors that you didn't create, and then you use these paths. Okay, you also use these paths when you configure the actors from the outside, etc. And you can even use things like, for example, if I'm inside A here, I can use actor4 dot dot slash star, what's going to happen then? I'm going to get all my siblings, right, on the same level. I'm going up on a hierarchy, and then I'm getting all the ones, including myself, right? There's going to be an actor selection that you can use to work with sets of actors and so on. So you can really navigate it like that, which is, I think, is pretty intuitive. If you use the Erlang, by the way, I mean, we've taken some of the best parts of Erlang, I think, but we also added some stuff on top of that and changed a lot of stuff that we didn't like, that the users found unintuitive and that didn't fit in the bigger picture. The second sort of construct is send. So we can create actors, we can send actors, and we can send message to actors, sorry. The nice thing with send is that it's completely asynchronous and non-blocking, okay? So some people also call it fire forget. So, and everything in Akka, in the terms of the dispatching, when you send a message to an actor, there's not a single lock in the whole hot path. Everything is completely lockless. That gives us extremely good performance and throughput, right? But even more importantly than that, from a semantics perspective, everything happens reactively, right? So everything is sort of, by default, everything is lazy, like sits doing nothing. And when an actor is doing nothing, he doesn't consume any resources apart from memory. He doesn't sit on a thread, right? So there's no real utilization at all apart from memory. So an actor sits doing nothing until a message is sent to him, right? Then he wakes up and starts doing stuff. So in a way, message is like the kinetic energy in an actor system. So actors can have a lot of sort of potential energy buffered up. They can be like ready to do a lot of important stuff, right? Taking over the world even. But they won't do anything unless they actually some things trigger them to start doing things. Create new actors, sending messages to them, and it trickles down into the system. And then everything goes down to like passive again. So it's extremely lazy, extremely resource sort of, we'll say, it's really very try to minimize the resource utilization as much as possible. So how do we send a message then? Then we use this actor ref. The actor ref have a method called tell that basically does what it says. It tells another actor to do something. Okay, so we can say greeter, tell, and then send in the command, and that's a message. And this returns immediately. This doesn't wait for the actor to like put things in his mailbox and for the mailbox to be processed, to have the message implied to the actor, and it returns immediately after putting the message on the mailbox. Okay. Then we have a concept of scheduler. That's what we call the dispatcher. We actually have many different dispatchers. The default one is usually best, but we have other specialized one that works great in other environments. So there is the concept of this global scheduler that uses different algorithm for that you can actually tune for fairness and how you want it. But it actually takes the message from the actor, wakes him up, puts in the message there, let him run, and then it's back to suspended. Okay. It does this all the time. So actors, of course, need to be tied to a thread to actually execute. So we can say that actors run on a shared thread pool or n number of shared thread pools, depending how you want to configure your system. So this is the full example, actually. This is all you need to start creating actor systems, right? Now, so this is all, if you don't do anything now, if you have no configuration file whatsoever, this just runs in process. It creates an actor in process and just runs it in process, right, on the single JVM. But let's now we perhaps want to say, oh, this actor called greeter here should run on another machine. So I want to start creating a cluster, okay? What's going to happen then is in order to make that happen, we just have to write a little piece of configuration file. This is Akka's configuration file. It has actually different sort of skins. You can use it. It looks like you can use straight JSON. You can use this like JSON style, more syntactic sugar. You can use property files, and so on. And it's all written in Java, by the way, because we use it to bootstrap Scala. So we have the same configuration format for Scala, Akka, and Play in the whole stack. So even if the only thing you use from this talk is this configuration library, I think you want a lot. It's really nice. Anyway, So the first thing we need to do now, if we want to like make a remote deployment of this, we want to change the topology to run on a cluster. We say, I want the remote ActorF provider. That's sort of the creator of the actors. It should be remote enabled. Then, see here, in the deployment section, we use the name here again. You remember, it was greeter, it's out of systems, it's a top level actor. Then we use /greeter. If it's a child to greeter, we say /greeter/ the child, the name of the child, or whatever. So we use these names here when we want to configure the system. So the only thing we need to do now is say, okay, I want this to be remote deployed, and then I tell it where. Okay? I'm using the Akka protocol. Then I'm defining the system, my system. I don't remember if you remember that, but we actually name the system there, my system, right? So all names matters. Okay, so we have the my system there. It runs on this machine, on this port, and that's something that I configure elsewhere in the configuration. All the ports that should be open for all kinds of for all the systems, right? And that's it. When I create this actor, what's going to happen now is it's not going to be created locally. It's actually going to be deployed to another machine and instantiated there. And the reference I get points to that guy. So if I start sending messages to it, it will travel across the wire over to that guy, and so on. So this is what I call by location transparency. And even better, the system can actually optimize things. For example, we use that in our adaptive routers, for example. That we have routers that sort of adapt according to the runtime metrics in the system, and then they can actually move actors around. The guy using them doesn't know. So he doesn't care, he just wants the most throughput, right? The third thing I want to talk about is become, okay? Become is where things get a bit funky in a way, and some people might wonder, okay, why would I ever want to do this? But it turns out to be very useful. So what become does is it redefines what the actor is. If you look at it from a type system perspective, it's like if the actor completely changed both interface and implementation. It really becomes something completely different. And why would I want to do that, right? One thing I want to add before I start giving examples of why and where it's really, really useful is that behaviors, as they are called then, are stacked, right? So I can push behaviors on the stack. And then I can go back to my original implementation by just popping the stack. That's something that's also very, very nice. So why would I want to do that? Yeah, let's say, for example, that I'm creating my system, all using like single actors that run. Okay, it might then later turn out that this actor is extremely highly contended. I didn't expect it to be, or I might expect it to be. It's just that most of the year it's actually not. But over Christmas it goes straight across the roof. Okay, then I can just configure my actor. So as soon as I'm getting loaded, my mailbox reaches a certain size, or whatever metrics I use within the actor to understand that I'm overloaded, I can just transform myself to a pool. Okay, I become a pool, and then I spawn up like 5, 10, 100 guys on some other machines or in process or whatever. And for the guy using me, he doesn't know that I turned myself into a pool. That's just something I can do internally. And when the load goes down, you just pop the stack and go back to become a single actor again. And you can probably shut down the EC2 nodes that you ran just during this peak, for example. Right? I also use it for implement state machines. I, for example, start with the behavior with just one interface, or with just one message called start, for example. When I receive that, I'm running. Then I might have my full implementation of the service, like 5, 10 messages. One of them might be resume or suspend. I run for a while, and then something wants to suspend me. It runs suspend, and I'm becoming suspended. That is one single interface, one single method called resume. When I get resume, I'm popping the stack, going back to running again. And then I might have something that I can go back to stop. And then that's the end of that, right? So you can actually implement state machines. Because not only behavior, but you can actually pass in the current state into the behavior as well to keep behavior and state across these different stages. It's a very intuitive, very nice way of dealing with state machines. And actors are often state machines. These actors should have state. completely stateless actors are sure useful, right? But where they really shine is where you decouple state and behavior. Because what I didn't say is that if you have mutable state inside an actor, that's completely fine. Nothing bad can happen. It's like enforced by the model to have that completely thread safe. Okay, you can have mutable state and hash map or whatever, and you never need to guard yourself, right? Which is very nice. You can also implement things like graceful degradation. Instead of transform yourself to a router, you might instead start throwing exceptions, like saying, "Oh, I'm overloaded," or you might actually want to start dropping messages, like piping them to some log file or whatever to see these are actually. Or you can send them to Akka's dead letter queue. We have a dead letter actor F that everyone has to handle. You can send them to that, and then you can add. Then they go out on Akka's event bus that we also have implemented for you. So you can just listen to these dead letter messages, pick them up somewhere else or whatever. Right? You can do things like spawning up a whole bunch of completely empty workers with no behavior and state at all, and then you can spawn up a master that just first starts sending out the implementation to all of these actors, right? And then it starts using them by sending out messages and aggregating the result. And when it's done, it just shuts everything down and makes sure that the actor pops their behaviors, they're all empty again. A new server can come in, start sending out his behavior, right? It's you can create this completely dynamic world. So it's really fascinating. Use your imagination, but there are many more use cases than this, but these are some of the most obvious ones, right? And how do you do this then? Yeah, in Java, we don't have closures yet, right? So it's a little bit ugly. You need to create an anonymous class with one method. But in Java 8, this will be nice. Then we'll scrap all this boilerplate. But for now, we need to create an instance of this procedure with the method apply. And here is where you add your new behavior. Okay? And we also have procedure that actually can take state in, so you can pass state along between your stages as well. So, load balancing. I just want to talk a little bit just load balancing. So now, for example, if you have this actor F, and you want to now create it as you want to turn it into like a router immediately, then you can just using on the props object, you can say with router, and you pass in the router, the number of routees, for example. You can also do this also from the configuration file. Or you can do this at runtime, depending on how you want to do it. You can also add, for example, a pool to a router. Say I want to have a lower bound and upper bound, just pass that into the round-robin router here, and then you get a router backed by a pool, and so on. And we have many different router implementations, like all kinds, random, consistent hashing, broadcast, you name it. We have a lot of adaptive ones that looks into like least memory, least CPU, least number of messages in the mailbox, and so on. It's nice in the cluster. So now, I'm going to talk a little bit about Java 7 concurrency and just show you how Akka is using Java 7 concurrency. There was a lot of nice stuff that was added and that really enabled us to get our performance numbers and throughput numbers across the roof. So first, like some of the new utilities that you have in Java 7, or one of the key things were the fork join framework. That is something that we now rely heavily on in Akka. We didn't before. In other words, it's thread local, random, and phaser, and so on. But we want to focus now on the fork join framework, okay? So the algorithm is pretty simple. You have fork and you have join, okay? Fork means that you like recursively fork off things, like basically, like you see here. You have a task that like forks off one other task here and one other task there, and that happens all recursively down like a tree. And then it awaits the computation. And when the computation is done, it joins it back to its parents, like trickles all the way up to you get the final result. It's great for like divide and conquer style algorithms, okay? It also uses, in the internals, it uses something called work stealing, right? So each of these workers have their own work queue. And when one of the workers run out of his messages, it tries to steal from the other workers. So and it actually turns out that this has had a little bit better performance and throughput than the classic standard thread executor service that you have. Another way I think as an example of a way to to use the fork join pool is through this parallel array. Other examples of fork join pool is like Scala's parallel collections relies heavily on them. That means that you can take any collection in the Scala library, a map, a list, or a set, or a tree map, or whatever you want, and you can just say .par. You're going to create a parallel projection, and that means that all transformation methods you pass in, like for each or whatever you do, would now be run in parallel, right? They are talking about if Java should add that. Java's copying all the good stuff in Scala. So this was sort of expected. So they talk about if they should add that to Java 8 or something like that. We also use it, as I said, in Akka. So how does we use it? It all started out with the benchmark on our 48-core box down in Lausanne. We bought this beefy box to really, see how Akka can perform on very good hardware. And we ran our benchmark. We weren't really pleased. Actually, it doesn't say you much this, but I will give you something more so you can see it in context. But for this typical benchmark, you can see it completely flattens out after about 7-8 actors or so. We couldn't get it any further. So then we switched to the fork join pool, and that didn't give us much more either. So then we started thinking, okay, what's the problem? It turns out that Dag Lea, he's the guy that wrote this. He wrote most of Java Util Concurrent. He's on our advisory board at TypeSafe, so we have pretty good connections with him. Okay. First, we just to show you in details what the problem was. Then when we ran it, I don't know if you can see here, but this is all red here. This tries to highlight that the context switches were just across the roof, more than 70,000 context switches per second, which is way more than it should be. Something was really bottlenecking. Okay, the question was what? So what we actually did was that we went to Dag and said, what's up with this? You were bottlenecking in your fork join pool framework, and he said, yeah, I sort of expected this to happen. I was just basically waiting for someone to run into this. And great, now I have a test case. Let's fix it. And it all actually turned out that no one had ran into this because no one had actually optimized the whole code, sort of exercised the hell out of fork joins that much, like we did in Akka. So no one actually hit this. But what Dag did, instead of the old fork join pool had the design of it that it's a single global queue. Then it had then each worker had its own queue. Okay, so then randomly, sort of each of the workers sort of took jobs from the global. But every time you dispatched a new job, it was to the global queue. Then you also have this thing of the work stealing. First you have the problem, you have the bottleneck in the single global queue. And secondly, you have this sort of a decision: each worker, should I try to steal jobs from some other one, or should I take from the global queue when I have run out of jobs? So what Dag was basically just completely get rid of the global queue, stripe it so each worker only had his own one, and use the thread local random to randomly assign to these. And what that made it happen is, here's the old benchmark. So it tops out after 1.5 million messages a second. With this change, that's actually not yet shipped in Java 7. We have sort of embedded our own fork join version inside Akka that has this fix. You see, it just goes all the way up to 20 million messages a second. Then after some even more benchmarking, as you can see over here, so the context switch is now down to 1,000 per second, which is where it really should be. And with some even more tweaking, both internally in the fork join pool as well as in Akka, we were able to push more than 50 million messages a second. And this was only the nice thing is that this wouldn't have happened if we wouldn't have been able to use the fork join pool and ran into this bug, so it could be fixed. And that's something everyone sure can benefit now. This fix will of course come in Java 7. So let's see how much time I have. We start 5 minutes late, so 10 minutes or so. Okay, so I just want to talk about the final thing, and that is how you deal with error recovery and failure recovery in in Akka. So first, I mean, if you look at failure recovery from a Java perspective, okay, I think it's completely broken. I have to say that. At least working now with a different, I think, superior way of dealing with failure. The problem is that in Java, C++, and so on, everything that using like threads as the core construct, unit of computation, you can say, is that you're giving a single thread of control. Okay? This means that if something blows up in your thread, what's happening? If you haven't guarded yourself, you will get like basically the only thing you get is a stack trace all the way up to your thread, new thread, or the Java executor service. Then it's like dead silence. It's impossible to find out, right? No other thread will ever find out that this thread blew up, because exceptions do not propagate across threads. So that means that in order to play safe, you need to do all your recovery in this single thread. The same thread as you do your computation, you need to do your error recovery. Okay? The bad thing is that this leads to extremely defensive programming. You basically have to add try catches all over the place to just feel safe. Okay, so so your business logic becomes very tangled with your error handling logic, and it's also everywhere. Right, since something bad can basically happen everywhere in the classic Java program, you need to have this try catch with error handling all over the place. Completely pollutes your whole software architecture. Okay, I really think we can do better. We can do better than this, and that is the sort of the modest attempt of the actor mold to solve. And I think it really does. It does deliver. People call that "let it crash" as the sort of solution to the problem, and that's where the fourth sort of construct comes in, supervise. So with supervision, you remember the actor had it like a tree, or created as trees. Each parent supervises its children. Well, what this means is basically that whenever something bad happens, for the guy that's actually running the code, he doesn't care. He just dies. Then a notification will be sent up to his parent, and he can take action upon that. So the business logic is completely free from error handling code. Secondly, it's configured rather than coded. It's all declaratively configured inside each of the parents, right? So one way of looking at it is that you create systems like an onion, okay? So your most important state, the state that you just can't lose, then it's like game over for your application. That you put inside, in the innermost of this onion, that's what you put there, okay? And then you layer levels of defense around that state, right? So the idea is that if I'm holding on to something precious, and I want to do some computation or ask some guy that might like yell and scream at me or something, I never do that myself. Instead, I'm creating a new actor. I'm delegating that to him. If he runs out on this minefield and blows himself up, that's okay, at least in my perspective, right? Because I can just create a new guy, try it again over here. And if that doesn't work, it might be better spawning up on another machine. Might be something funky with, I don't know, with Nick here, if we're talking through an external service or something like that, right? So you layer these levels of defense. You never do anything yourself. You delegate, okay? So instead you create your architecture system similar to this. We talk about something called the error kernel. If you Google for it, you will find hits like that's sort of the way of talking about this center of the onion. That's my error kernel. That's the stuff that I just can't lose. And then I just create levels of defense. So now if a request comes in here, for example, something terribly happens, it blows up. What's going to happen? A notification will be sent up to his parent, running in another thread now. So exceptions propagate across threads nicely, like they should. He can take action upon that and just restart the guy. It might be that a group of actors together implement some sort of service. They are like implicitly coupled. It might be that I just can't just kill one. Then you can group them and say, okay, if one, then all. It's called the all-for-one strategy, like in the Three Musketeers. It might actually be that this guy, his parent, he can't deal with the error. It might be above his pay grade to actually do something about it. What's going to happen then? That he will just kill his whole subtree and escalate. Hopefully someone higher up will have the knowledge, power, or whatever to deal with the problem. Okay? It might be that it's like out-of-memory error. Then it will hit the error kernel. It's not really any chance to recover from that. But that is like an exception. It's very unusual. Normally, most errors are able to recover from, and what you get here then is a system that can heal itself. It can actually deal with its failure by itself. But if it hits the error kernel, then if you run more than one box, then you're still fine, because you can actually link across machines. So you can actually take your actor tree and put them out on different boxes. You can link them, and they will get notified even though they're running on different machines. And by default, each actor actually has a default like supervisor strategy that if you don't do anything, you're usually fine with the defaults. But it can be overridden, and the way you do it is like this. It's a bit ugly from Java as well, I have to say, being used to Scala. But basically it's a DSL here. The gist of it is here, right, in this apply. The rest is just boilerplate, basically. So you can see if the exception that comes in here is an arithmetic exception, then it says it's a resume. That's sort of the directive for how we should deal with the actor that failed. If it's a null pointer here, it should restart. Else it should escalate, meaning propagate the exception up. And apart from that, it's just a regular actor. And actually, this applies then to the guy that's created out of this context, and to his children. Okay. And from the guy's perspective, this is in Scala, by the way. I didn't have time to rewrite this. I apologize. But basically, it looks very similar. Basically, you have chances of hooking into callbacks. You can do something when I'm started, after I'm started, after I'm restarted, before I'm restarted, after I'm killed, before I'm killed, and so on. So there you can hook in, like, and do things like cleaning up resources before, and like reinitializing yourself after the restart, and so on. So this was Akka 2x. At least when it comes from the actor's perspective. There's much more to it. I don't have time to go through all of that today, since I'm running a little bit behind. But it has a lot. It has a completely brand new cluster module, for example, that's coming out in 2.1 that gives you the elasticity. Then really nodes can come and go. Just cluster membership, so you can subscribe on events. It has all these adaptive routers that will automatically, if 5 nodes come along, it will just automatically spawn up new stuff on those. So if nodes leave, they can be moved over and stuff like that. It has an event bus. It has like great integration with a bunch of frameworks, like Apache Camel, for example. You can use Akka's actors as Camel endpoints to just talk through them over to Camel and receive messages through Camel. Or use ZeroMQ, for example, and we have many different ways of dealing with concurrency also, where actors is not a good fit. So for transactional memory is one. We have something called data flow concurrency. We have a great futures library that's nothing close to the extremely crippled version there's in Java Util Concurrent that I encourage you to take a look at. So this was basically it. I had some slides on the clustering as well, but I won't have time to go through those. So basically, if you want to learn more, go to akka.io. We have about 400 pages reference documentation, so pretty much everything should be there. Join the mailing list, ask questions. All stupid questions are very welcome. We'd love to have you part of it. There's a whole bunch of great blogs out there. We had a thing called Akka Summer Blog, where we encouraged the community during the summer to write blogs for the Akka team blog, and there was more like 8 or 9 different great blogs about how to use Akka in the real world, how people actually use it in the real world, and so on. If you want to look for more like to support the training, we have Akka training and stuff. If you want, that's for pay, of course. Everything else up to now is free. By the way, that's the only thing that you can find stuff that we actually have to pay, like support, like training and stuff. But that might be useful as well. So that was everything I was planning on sharing. Yeah, I'm here rest of the day. We don't think we have time for questions now, but please come up to me outside here, or would you grab me over the party tonight or so. I'll explain more if you want. Thanks.